Good afternoon. My name is Tim Gallagher. I am part of Team Alpha along with Patty Homan and Tim Webb. We researched thorium reactors for our project. This quickly turned into a large report, so we ended up breaking the team's responsibilities into three main categories: thorium technical data, current thorium research and applications, and arguments for and against thorium as a fuel. My responsibility was the technical piece, and so that'll be the focus of this presentation. A lot of what you'll see in both our research paper and in this presentation is a comparison between thorium and uranium-235. And there's a good reason for that. Most of us are quite familiar with uranium-235 reactors. They do comprise the majority of the nuclear fleet throughout the world. So it serves as a good reference point when describing the technical aspects of thorium to use uranium-235 as the reference point for that. There is a PowerPoint presentation that goes along with this recording, so if you'll follow along, I'll be calling out slides to go to throughout this video. On to our first slide, thorium technical data. Nearly 100% of naturally occurring thorium is thorium-232. 6 naturally occurring isotopes do exist, but only thorium-232 is stable. It's relatively abundant on Earth, about 3 times more abundant than uranium, which puts it as about as abundant as lead. Thorium-232 itself is not fissile, it's fertile. Thorium-232 will absorb a thermal neutron, become thorium-233. Thorium-233 beta minus decays into protactinium-233, which then further beta decays to uranium-233, which is our fissile element. Half-life of thorium-233 is about 22 minutes. Protactinium's half-life is around 27 days. The uranium-233 fission equation is very similar to that of U-235. U-233 absorbs a thermal neutron, becomes U-234, which fissions into 2 fission fragments, yielding 2 to 3 neutrons. Next slide, we can compare the probability of fission as well as the energy released from fission and the neutrons released from fission between U-233 and U-235. We do that using the microscopic cross-section for fission of U-233, which you can see there is 531 barns. For U-235, it's 585. The energy released from fission for U-233 is 181 MeV compared to 187 MeV for U-235. So U-235 does have a slightly larger energy yield from fission and a slightly better chance of fission, but because it is so close between the two, that means that the operating characteristics between the two will be similar in similar neutron fields. On to the next slide, we start to see an advantage towards U-233, and this is with the reproduction factor, which is a term used in the 6-factor formula. It describes the number of neutrons released on average from a single fission event. The reproduction factors displayed here are for U-233, U-235, and plutonium-239, which is a major fuel source near the end of core life or core cycle in a U-235 reactor. Also displayed here are the thermal, epithermal, and total reproduction factors for each one of those isotopes. You'll notice that in all cases, U-233 has a reproduction factor above 2, and it also has the largest reproduction factor for each one of these isotopes. This makes it a reliable breeder. That is to say, there are sufficient neutrons from one fission event to not only create additional fission events, but also to breed the U-233 fuel. Our next slide is a summary chart of relevant data for the elements in the thorium fuel cycle. It's shown as a snapshot and interesting discussion points. These are all of the isotopes that could potentially be found in a thorium-232 reactor. Some interesting discussion points. The first is the large total cross-section of thorium-233. This is a problem for thorium because it means that there's a very large chance that thorium-233 will absorb a neutron and become thorium-234 instead of decaying to protactinium-233. This is a problem that's addressed with both MSRs and LFTRs, which will be discussed subsequent to this. It's a design problem that plant engineers need to account for. Interestingly enough, though, if thorium-233 were to absorb a thermal neutron, the end result would be breeding fertile U-234 through the thorium-234 decay chain. U-234 would then breed U-235 and add to our total fission inventory. Another interesting path would be for resonance absorption of U-235. It's a problem that's recognized in U-235 reactors and is why the moderators and the moderating ratios are set up the way they are. If U-235 were to resonantly absorb a neutron, become U-236. U-236's decay mode is by alpha decay, which if you wrote out that equation, you discover would yield thorium-232, which was our initial breeding fuel. So it would end up recycling back to the initial starting point. In summary, to take away from this table is that by using thorium-232 as a starting point instead of U-235, there's multiple ways of achieving fission. One is through U-233, of course, through U-235, and then subsequent transuranic fissions that normally occur in a U-235 reactor. We're going to move on and discuss two of the more interesting types of thorium reactors that exist. Molten salt reactors, or MSRs, and liquid fluoride thorium reactors, pronounced LFTR. On the next slide, we'll find a block diagram of an MSR. The salt in the primary loop is infused with nuclear fuel, which directly heats the molten salt. The heat is transferred via a secondary loop of salt and a heat exchanger. Secondary loop is circulated through another heat exchanger, which is connected to either a Rankine cycle steam plant or a Brayton cycle gas turbine plant. The Brayton cycle is what's shown here in this depiction. Should the need arise to quickly shut down the reactor, the freeze plugs in the system will melt. The molten salt solidifies in the emergency dump tanks. This process can be reversed whenever the plant is ready to start up again. This diagram shows a particular type of MSR on the next slide. It's called the liquid fluoride thorium reactor, or LFTR, as we said before. It's another two-salt plant design, allows for breeding of U-233 to occur. So trace this out with me if you would. The core, the central yellow portion, it's initially loaded with a fissile mixture, U-233 or 235. The fuel mixture fissions, releasing heat, of course. The heat is transferred out through the heat exchanger into either our Rankine or Brayton cycle gas plant. The salt is then returned through the refueling and fuel processing part of the system and back into the reactor core. When the U-233 fission event occurs, some of the neutrons will be used for fission, others are allowed to bombard the blanket salt loop, and that's the outer green portion there surrounding the core. Thorium-233 will of course absorb a thermal neutron, become thorium-233. Thorium-233 is then allowed to move to the decay tank. It will beta decay, like we talked about, to protactinium-233 and finally U-233. Any remaining thorium is allowed to return back to the blanket. whereas the U-233, once it has sufficiently decayed, will move into the fueling processing portion of the system as you trace out the arrows. It's then allowed to enter the reactor core, and the cycle is then repeated. Some advantages we'll talk about quickly of thorium. The fuel currently exists in two primary forms. One is solid fuel pellets, which we're used to in current reactor designs, and also as a molten or liquid fuel. Mixed oxide fuel pellets are currently being produced by Thor Energy as a replacement fuel for uranium oxide. This accompanies with it a few advantages. One is that thorium oxide has one of the highest melting points of all metal oxides. If you replace uranium oxide with thorium oxide, it raises the fuel melting temperature from around 2800 degrees Celsius to around 3300 degrees Celsius. Additionally, replacing UO2 with thorium oxide increases the thermal conductivity of the fuel by 150%, up from about 0.02 to 0.03 calories per second centimeter squared. Utilizing thorium in a molten form presents certain solutions to classic nuclear problems, namely the core meltdown. With the reactor fuel infused in the molten salt, there's no solid fuel pellets to melt down, thereby making a core meltdown scenario actually impossible. Additionally, lifters operate at atmospheric pressure due to the low melting point of the fluoride salt mixture. This means that core ejections are also impossible due to a vessel breach in a reactor accident because there is no differential pressure between the reactor vessel and the containment building itself. That was the end of my presentation for thorium technical data. Next up are Patty Homan and Tim Webb. They'll be discussing the advantages and disadvantages, arguments for and against thorium, and also current research into thorium reactors. Thank you for your time, and hope you enjoy the presentation.